All right, it's 1:10. Let's go ahead and get started. All right, so exam 3, you guys took it last week. On Friday, Brian went over it with those of you that came. I understand there were about 10 of you. Is that about right? 10? All right, so if you want to look over your exam, I'll have it during my office hours. I've got office hours right after class today at 11:01. If my office hours don't work, send me an email and we'll set up an alternative time to look them over. So overall, the exam score was not bad. I mean, the average was around 76%, and the median was at 77, so half the class scored 77 or above. Looking at the breakdown, around 13% of the class got an A on the exam. Looking at 21% for B, the B range, and close to 40% for the C range. So despite the fact that the average was lower than the previous two, it was pretty good overall. And then looking at the combined average for exams 1, 2, and 3, going into the final, it looks like our median is around 82. So half the class are in the A, B, and C range, right? Or A and B range, I should say. So that looks pretty good. Right, do be aware, final exams, cumulative. Because they're cumulative, they have a tendency to have a lower average, right? It is time for us to think about the final exams. Come on. All right, so the first event of significance is the optional standardized exam. If my brain's working properly, that's a little over 2.5 weeks from now, around 2.5 weeks. So it's Thursday night, 6:30 to 8:30. It's optional. I wanted to talk a little bit about why I'd like you guys to take it. The big thing is, if you're well prepared for that, then the final exam in here should be a piece of cake, should you choose to take it. Incentivizing, 2 points extra credit if your score on that is within 2 standard deviations, so that's a typo of the average. So that's just to encourage you to think when you get there, right? Not just come in and put your name on it. If your percent score on the standardized exam is higher than any of the other exams that you have taken or will take in this class, it will replace those. So this is a good place to get some advancement in your grade. And then if you do really well on it, you don't have to show up for the final. So let's say you have a goal of getting a B out of the class, and if on the final exam, on the ACS exam, you get 80%, well, that wipes out any other previous exams, and you're set to go, okay? All right. On the other hand, if you get a 95 on it, that wipes out everything previously, and you get an A in the class, right? Pretty much, assuming you did some of the homework. Yeah? So, one of the reasons that we're testing it is to get those things. Historically, averages are in the 50s. That being said, last semester, I have to look exactly, but we did above the average. Our class did. So, and you guys have been above the average, above that class average. So, but those ACS exams aren't pieces of cake, right? Okay, so then the final exam is going to be during finals week. So if you are registered for this course, for this section, you'll take it on Wednesday afternoon. If you are registered for the 10 a.m., you're going to take it on Tuesday morning. If you have some conflicts or need to have a rearrangement, you need to get in touch with me before the Friday before Dead Week. All right. Okay, so things that we have talked about previously. We've introduced Helmholtz and Gibbs energies, right? And the big reason for doing this is that we've shown that the Gibbs energy and the Helmholtz energy predict spontaneity based on system parameters only. So if I know delta H and delta S for my system, I know whether the process will occur or not for a constant temperature and pressure situation. If I know delta U and delta S, then I know under constant volume circumstances whether a process is going to be spontaneous or not. We've also shown that delta A and delta G are related to the maximum amount of work that we can get out of the system. Delta A is the work that I can get in general, and then delta G is the non-pressure volume work. We have previously introduced Maxwell relations as cross derivatives that give us identities. We're going to be applying those today's lecture and continuing that on Wednesday. Right? So we're going to be continuing our discussion of Maxwell equations. We're also going to be talking about natural variables, which we've introduced previously. All right. From there, we're going to ask, how does entropy depend on volume? Right? And one of the things that I'll just highlight at this point is that previously we've calculated delta S for the isothermal expansion of an ideal gas, right? We're going to repeat that, but now looking at it from another direction, okay? All right, then we're going to ask the question, how does the energy depend on the volume? How does the enthalpy depend on the pressure? And you may step back and say, well, we know that for ideal gases, U is dependent only on temperature, right? We're going to be deriving expressions that are completely general. They don't need to be ideal gases. They don't need to be gases. Okay? Right? And then enthalpies on pressure we'll look at. And then we're going to end today looking at the Gibbs dependence on pressure and temperature. How many people have heard of the Gibbs-Helmholtz equation? No one? Okay. All right, I thought that showed up in 178. I'll have to go back and look. But at any rate, the other thing I wanted to just point out, we've seen that we've been doing some parallel derivations. We're going to continue that trend today. So up to this point, we've seen that dA indicates spontaneity when I have a constant temperature volume situation. And then stepping back from that, I know that if I have constant volume and I only have pressure volume work, at constant volume, the heat transfer is the same as the change in the energy of the system. One of the things that we'll see is that the Helmholtz energy has natural variables, temperature and volume, and then we can talk about the dependence of the energy of the system on volume using the Helmholtz energy. All right? Okay. In a parallel derivation and thought process, we're going to look at dG. We know that that's going to predict spontaneity for temperature and pressure, constant situations, and we know that constant pressure heat transfer is the same as the enthalpy change. So what we're going to see is that, and this is where we have consistency, temperature and pressure are the natural variables. Up there, temperature and volume are the natural variables. And then we'll see that Gibbs can be used to determine the relationship between enthalpy change and changes in pressure. Okay? All right. Starting point today. Okay, so where we ended last time was we've shown that delta G gives us the non-pressure volume, non-expansion compression work that's available to a system. And just to make sure that we understand, this is the maximum that we can get. So if W is in actuality less than 0, that means my process is producing work. It's doing work. Right? In that case, we can say the absolute value of delta G is going to be greater than the actual work realized. Right? And then if, on the other hand, I need to do work on the system to get it to occur, then we can say that the absolute value of delta G represents the minimum work that I need to do to get the process to occur. All right, so a very quick example. So we can ask the question, what's the amount of energy that I need to take a mole of water at 1 atmosphere and decompose it into its constituent elements, right? So back in general chemistry, Chem 177, you probably did this in lab and saw it as a demonstration. Right? In order for us to answer the question, we need to calculate what delta G is. Right? So before we talk about specifically how we do that, I want to mention that we have two different ways to get there. One is that we know that delta G is equal to delta H minus T delta S. Right? And so that says I can go to a table of thermodynamic data and I can use delta H of formation to get delta H of our reaction. And I can take standard molar entropies and use that to get the entropy change of our chemical reaction. And then I can plug that in to our definition of delta G. Alternatively, if we go to tables of thermodynamic data, what we often see is delta G of formation for for elements or for compounds, all right? So you'd have a table of standard molar entropies, enthalpy changes of formation, and Gibbs energies of formation. And what I can do is I can use delta G of formation to get delta G of the reaction, just as we've done using Hess's law. My voice is giving out. If you guys are lucky, it'll get out before the end of the lecture, right? How many people know sign language? No one? Not going to fly, I guess. Okay, so at any rate, if I go to the route where I want to use the Gibbs energy of formation, I have values for water. And if you think about what we're asking, we want to take water, decompose it into constituent elements. Well, that's just the reverse of the formation reaction. So that delta G naught of formation is the opposite of what we're interested in. All right? So I can flip it around, and we know that if we flip it around, that changes the sign. Right? And so without doing any calculations, I can say that 237 joules of work, in this case it would be electrical work, is needed to drive that reaction. Okay? Make sense? All right, section 3, actually the next 4 sections, I guess, we're going to be talking about Maxwell relations. All right? So in this case, we're going to use Maxwell relation that we get from the Helmholtz energy. And one of the things that we're going to show in this section is something that we already know, all right? And that is U for an ideal gas is not a function of the volume, right? So you may think back, whenever we've been talking about changes in energy of our system, we've said for an ideal gas, it depends only on the temperature. So if I change anything, or the number of moles. So if I hold temperature and number of moles constant, that means the volume can't impact that energy. And we'll show that explicitly today. All right, and then the goal behind our Maxwell relations is we're going to be getting some identities. And those identities are useful to us because they often will give us some thermodynamic relationship in terms of parameters that are experimentally easily measured, or that I could easily determine from an equation of state. All right, so in this case, we're going to work on the Helmholtz one. We're going to start with the first law. So we've done this sort of thing before. We know du is given by dq reversible plus dw reversible, right? So this is the change in the energy of our system due to the heat transfer and work transfer energy changes. If I limit our discussion to pressure volume work, all right, and introduce the idea of entropy, I know that dq reversible is the same as TdS. And then work will be minus PdV. Okay? All right, so what that tells us at this point, well, actually, we're going to use that in a moment. All right? So now we're going to go to our Helmholtz energy. I'm going to start with that definition, A equals U minus TS. I'm going to differentiate it. That's going to get me dA is equal to du minus. Now I've got the differential of temperature times entropy. All right? That's a product. So that means I need to say minus TdS minus SdT. Right? So I've used the product rule. Okay? All right. And now what I can do is I can substitute in du from this equation. All right? And we see I've got TdS in 2 places, and that's going to cancel, right? Because they're opposite sign. All right? And so what I'm left with is minus PdV minus, whoops, S dt. Okay? All right, so let's step back and look at this differential equation. This says the change in our Helmholtz energy is caused by a change in volume and a change in temperature, dV dt. Okay? That tells us that A is a function of V and T. And as soon as I know that A depends on T and V, I can do a total differential and say dA will be the change in the the Helmholtz energy due to a change in the volume holding temperature constant times dV. All right? And then by comparing this with this term, I've got dV in two places. That tells me dA dV has to be minus P, right? Because this is the same as this term. Okay? All right. So this is saying if I change the volume only, this is going to be the impact on my Helmholtz energy. Right? My next term will be dA dt, the other variable, times dt, and I need to hold the volume constant. Right? Then I can compare this directly with this, and that tells me that dA dt is the same as minus S. Okay? All right, so I'm just going to talk this through because we're not going to apply this particular one. But this gets us an identity, so if I have a derivation that has dA dV in it, I know I'm going to be able to replace it with minus P. Similarly, if I have dA dt, that's the same as minus S. Okay? Further, this tells me the dependence of A on V, right? Because I can rearrange this and say dA is equal to minus P times dV. Okay? Make sense? All right, so up to this point, we've just derived an expression for dA in terms of volume and temperature. Now I can step back and say, are these derivatives simple functions? Is dA dV simple? Yeah, it's about as simple as you can get. dA dt, right? Because they're simple, then we say that these variables that Helmholtz energy depends upon are the natural variables. All right? Okay, we haven't done any Maxwell relations yet because we know a Maxwell relation is the cross derivative. All right? So let me talk this through. dA is a differential equation, right? That's a differential equation. And because Helmholtz energy is a state function, that means I have an exact differential. And if I have an exact differential, the cross derivatives are equal to each other, right? We've shown that previously. So in this case, our cross derivatives will be minus dP, right? And what am I going to take the derivative of P with respect to? I need the cross derivative. dt. And I'm going to hold what constant? V. Right? Because minus P is dA dV, and I need to take the derivative of this with respect to the other variable, which is T. Right? And that in turn is going to be equal to, help me out, the derivative of S and minus S specifically, right? And with respect to V, holding T constant. All right? Now I've got a negative on both sides, so I can multiply through by minus 1. And this says dP dt at constant volume is exactly the same as ds dV. All right? So if you went into a laboratory and wanted to measure one side, which side would you measure? You'd measure the pressure and temperature, right? That's what we're looking for, pressure-temperature relationship. So this is easily accessible. We don't have anything that directly measures the entropy, right? Okay, so we'll see that provides a useful identity for us. Okay? All right, and then a little bit of foreshadowing. we're going to be, right now, we've shown the Maxwell relation from the Helmholtz energy. We're going to introduce the Gibbs enthalpy and total energy of the system Maxwell relations. Okay? All right, so the other thing we can do is we can focus on this Maxwell relation, right? And say, well, if I hold that temperature constant, I can say that ds is given by the derivative of the pressure with respect, to T, holding V constant times dV. Okay? And this basically says, this gives me the entropy dependence on volume. All right? And I can integrate that, and that will give me delta S is equal to the integral from V1 to V2 dP dt holding volume constant dV. Okay? All right. So we know that we can measure pressure-temperature relationships in the laboratory, but we also know that if we have an equation of state, we can write it in terms of pressure equal to, right? Think about ideal gas equation. P equals nRT over V, right? So I can take the derivative of that pressure from the equation of state and determine the entropy dependence. Okay? So we're going to look at the example for the isothermal expansion of an ideal gas, right? And before I do that, let me just point out, this is completely general. Nowhere in there have we said you have to be a gas, you have to be a liquid or a solid, you have to be ideal, right? So it works for all systems, okay? But now what I'm going to do is I'm going to say specifically ideal gas isothermal expansion. Well, that means I need to take dP dt. We've said that's nRT over V, right? The derivative of nRT over V with respect to T is nR over V. If I don't change the number of moles of gas, I've got N out front in front of the integral. R is a constant, and that leaves me with the integral of dV over V, which we have previously shown to be ln V2 over V1, right? So, and we've seen this before, okay? All right, the other thing that we can talk about is that we can use this relationship to look at deviations from ideal behavior, right? So if we think about it, ideal behavior, we have said probably from day one, occurs as P approaches 0, okay? So in the limit as pressure approaches 0, I have ideal gas behavior. As the pressure is decreasing, what's happening to the volume? It's increasing, right? So we'll just say V bar, and that's V bar, and V is getting large. Okay? All right, so in looking at deviations from ideal behavior, I'm going to be interested in delta S, which would be an entropy that depends on the temperature and the volume, minus what we call the ideal entropy, right? And I can calculate that ideal entropy simply by using a large volume as my comparison. So V ideal, where V is very large, to whatever volume I'm interested in, and then dP dt at constant volume times dV. And that's for experiments or equations of state, right? Graphically, that's what's shown in this plot, all right? So this is rho, which we've seen is 1 over the molar volume. So when we're at 0, that means molar volume is really, really small because it's reciprocal. So where we cross this axis is S ideal. And all the points other than that origin is going to correspond to deviation from ideal. All right? So this relationship gives us deviations from ideal for entropy. Okay, so next up on our agenda is to look at the relationship of the system energy on the volume. And again, we're going to start absolutely general. All right? Okay, so if I want the dependence of U on V, that means I want du dV. Okay? All right, so we're going to start with our Helmholtz equation. And that means I'm going to take, and we see we've got A equals U minus TS. So because I want du dV, I'm going to take the differential with respect to V for the entire equation. That gives me dA dV at constant t is given by du dV at constant t, right? And then I look at Ts, temperature's being held constant, so when I take the derivative, that comes out front, and so I'm left with minus T times the derivative of S with respect to V, holding the temperature constant. Okay? All right, I'm interested in this term, so I need to do a rearrangement, which basically means I add T ds dV to both sides. That gets me here. Okay? All right, so now we go back and we think dA dV. We have an expression for that, right? If you go back to where we started today, dA dV is the same as the pressure, negative of the pressure. So that means I can replace that with minus P, right? And then I have plus T. And then ds dV, our Maxwell relation tells us ds dV is the same as dP dt. So dP dt at constant volume. Okay? All right, so again, the importance of what we're doing. I have this expression for the energy dependence on volume. This is not something that I can easily get at from experiment. This is not something that I can easily calculate from an equation of state. Similarly here, I've replaced those quantities with things that we can easily measure or get from an equation of state. All right? Okay, and then again, this is completely general. If I use van der Waal equation, I expect to see something different than what I expect for the ideal gas. Right? All right, so then the question is, how do we determine the relationship between U and V for an ideal gas? Right? We already said that what we expect it to be, right? But basically, I start with our general equation. For pressure, I put in nRT over V. Right? I take the derivative of that quantity with respect to T, and that becomes nR over V. Right? And nRT over V is the same as pressure for an ideal gas. Right? So this is P ideal. And so I'm left with P minus P, or 0. Okay? All right, the other thing that we can do is we can use this to help us look at deviations from ideal behavior. Same thought processes as we saw for entropy. Right? If I'm looking at du dV, I can rearrange this. This will get me the dependence of U on V. Right? And when I choose to do the integral, I'm just going to choose a very large volume. That's my ideal case. And then whatever volume I end up with represents the deviation to the non-ideal region. Okay? All right, so another application. So in homework 12, you showed that the difference between constant pressure heat capacity and constant volume heat capacity is given by this expression. Right? And one of the things that we see that we have in here is du dV. Right? Again, stepping back for a moment, dV dt, in order for me to get that, I need to know volume as a function of temperature. Du dV, not easy for us to get, but we've just derived an expression for that. Right? So we know that this is the same as this. Right? And so putting that together, I have P minus P plus T. Whoops, that's not a T. Plus T times the partial of P with respect to T at constant volume. That whole quantity is multiplied by dV dt, holding the pressure constant. All right? And we see that our P's cancel, and we're left with temperature, dP dt at constant volume times dV dt at constant pressure, right? And now this expression is pretty straightforward for us. We know that we can get this information from experiment, or we can get it from an equation of state, all right? This is general. Doesn't have to be in the gas phase, right? So it's solid, liquid, you name it, it works. Now we know for an ideal gas what we expect it to be. Does anybody remember what the difference between Cp and Zv were for ideal gas? It's R for the molar heat capacities, and if it's not the molar heat capacities, it's Nr, all right? So let's see if that's what we get, all right? So I'm going to bring my temperature. We know that P is nRT over V. So the derivative of nRT over V with respect to T is nR over V, right? Before I do the next derivative, let's stop for a moment. nRT over V, what's that the same as? That's the same as pressure for an ideal gas, right? And then I take the derivative of V. Let me write V is equal to nRT over P. I take the derivative of V with respect to T. Well, that's going to get me nR over P, all right? I've got P over P times nR. That gets me nR. Make sense? Okay. Okay, so section 4, more Maxwell equations, more Maxwell relations. In this case, we're going to be looking at the Gibbs energy Maxwell relations, right? And this thought process parallels the previous section. We're also going to see that H is not a function of pressure for ideal gases. All right, so that's the corollary to the last one where we showed that the energy of the system is independent of volume for ideal gases. Okay? All right, so we're going to start with our definition of the Gibbs energy, H minus Ts. We know that H is U plus PV, and then I'm going to subtract Ts from that. So that means the same thing, right? I want to get that in differential form, so I can say dG is given by du plus, now I've got the differential of P times V, so that's going to be PdV plus VdP, right? Because it's a product rule. Plus PdV plus VdP, right? And then I've got minus Ts, differential of that, product rule, minus TdS minus SDT, okay? All right, we see du shows up in here again, and we've just shown that du is the same as TdS minus PdV. Okay? So, if I plug that in, TdS minus PdV, we see plugging in for du, we expect PdV to disappear, right? And what other term will disappear? TdS. And what I'm left with is VdP and minus SDT. So dG equals VdP minus SDT. Okay? All right, so again, this tells us the change in the Gibbs energy caused by change in pressure, change in temperature. So G is a function of T and P. And so I can do a total differential, right? So I got dG, dt times dt, dG, dP times dP, right? And what would you say about these derivatives? dG, dt, well, let's ask that question. What's dG, dt the same as? Somebody? dg dt times dt, yes, thank you, minus s. And dg dp is the same as volume, okay? Right, dg dp is the same as vdp, right? So I got volume. You got that? All right. I think we're going to send some sugar around. Okay. So when I look at dgdp and dgdt, are those functions simple? They are, all right? And so that tells me that t and p are the natural variables of the Gibbs energy, okay? All right, so the other thing that we can look at is dg dt is given by minus s, okay? That says dg equals minus s dt, right? So this basically allows us to get the Gibbs dependence on temperature, right? Make sense? These equations we're going to see are pretty important when we talk about phase diagrams. Okay? All right, so everything that we've created some, or identified some identities. We haven't yet done the Maxwell relation. Okay? So my Maxwell relation will be the derivative of something with respect to something else is equal to the derivative of something else with respect to something else. So what's one of the possible terms that I can be taking the derivative of? I need a cross derivative, right? So it's going to be derivative of minus s or v, right? So I'll choose minus s. What am I going to take the derivative of s with respect to? I need the cross derivative, right? So it's going to be the derivative with respect to p. And I'm going to be holding temperature constant. My other derivative will be dv dt. Thank you. And then what am I going to be holding constant there? P. Why did I write s? I think I heard somebody say it. All right, so if I choose to hold temperature constant, this Maxwell relationship will get me the relationship between entropy and pressure. All right, so that basically means a little rearrangement. I can say ds is equal to minus the derivative of the volume with respect to t. Derivative of volume with respect to t. Oh my gosh, what am I doing here? What am I doing here? P's constant. And then times dp. Right? To get from this differential relationship to delta s means that I need to do an integration. So this would be minus the integral from p1 to p2 dv dt at constant pressure dp. Okay? All right, so that means, of course, if I'm interested in looking at deviations from ideal behavior, I'm going to be looking at deviations from S at pressure approaching 0, right? That's this point. So that's S ideal, because we expect ideal behavior to occur as pressure approaches 0. And this can be calculated from here for deviations from ideal. Okay, so we can determine the dependence of S on P and the deviation from ideal. All right, and just as we did previously, we're going to look at the relationship between enthalpy and one of its natural variables, right? Pressure. All right. Previously, we looked at the dependence of U on V, right? So if we start with our definition of the Gibbs energy, if I want to know the relationship between H and P, that means I need dH dP. So I'm going to take dG dP. We're going to hold temperature constant. And if you think back, we've just shown that dG dP is the same as the volume, right? But we'll do that substitution in a minute. That in turn is going to be equal to dH dP at constant T. That's what we're interested in isolating, right? And then minus the temperature ds dP at constant T. And again, the temperature comes out in front because we're holding temperature constant, right? Okay, so now I have this equation. I'm going to rearrange for dH dP, and I'm going to do my substitutions, right? So we've seen that dG dP is the same as volume. ds dP, we have just shown, is the same as move. ds dP is the same as minus dV dt. All right, so I can put that all together, and my general relationships will be dH dP at constant T is given by the volume plus, whoops, not plus. All right, so I got a negative. I'm putting this in here, negative of a negative, that gets it a positive, right? And then to isolate it, I have to subtract it from both sides. So I have minus T dV dt at constant pressure. And again, everything that we've derived up to this point is completely general. Okay? All right, and then the other thing that's important is this gives us our enthalpy dependence on pressure as a function of easily measurable or calculable values. All right, then to make it specifically about an ideal gas, then I start with the general equation. I say, well, for an ideal gas, V is the same as nRT over P. And I can rewrite V minus T, the derivative of nRT over P with respect to T will be nR over P. And nRT over P for an ideal gas is the volume. And so that goes to 0. Okay? All right, so again, what we've shown is that the enthalpy doesn't depend on pressure for an ideal gas. In an upcoming homework assignment, you'll be doing this similar thing, but now for a non-ideal gas. Okay? All right, section 8.5. This is sort of a summary of some Maxwell relations. And because we've been talking a long time and because I'm listening, whoops, I'm boring myself. We're going to let you guys work on some things. We'll do the first question together, and then the rest of it will be, there's you guys a team of 3. I don't know how you guys are dividing up here. Are you a team of 4? 2 teams? Well, I meant the one down there. On the row, yeah. And could you pass one behind you? There you go. I don't know how you guys are grouping here, but I'll just hand these out like they're candy. All right, well, let's do the first one together. So as I've mentioned earlier, we're going to be looking at Maxwell relations for U, H, A, and G, we've completed our discussion of Helmholtz energy and of the Gibbs energy. So if we look at the energy of the system, so this says U is a function of entropy and volume. This T is du ds. And this minus P is du dV. Are those functions simple? Yes. So what's the natural variables for the energy of the system? S and V, right? Because U, the energy of the system, is a state function, the cross derivatives are equal to each other, so that means the derivative of T with respect to what? V, holding what constant? S, is going to be the same as minus the derivative of P with respect to S, and now holding volume constant. All right? This is the Maxwell relations. These are the natural variables. And then the rest of it, you're on your own. The answer will be posted after class with the annotated lecture notes. We're not done. Not yet. So please try to take 2 minutes or less. It happened at funerals and weddings. You guys done? All right. Are you guys done? Thanks. You're good. So you're taking home a souvenir, right? I'll come back. All right, please wrap it up. Thank you. Thank you. We got it? Okay, we still have a minute, so let's use every moment. So in the next 2 sections, which you guys, I know it's hard today. I know it is. I can feel it. It's hard for me too. We got a job to do. What we're going to do is we're going to look at temperature and pressure dependence of the Gibbs energy. All right? So our starting point is looking at dg dp is equal to v. We've just shown this to be true. I can rearrange this and say dg is equal to v dp. So if I limit our discussion, this is general, if I limit the discussion to a mole of an ideal gas, that basically says delta G per mole will be given by the integral P1 to P2 nRT over P dP. Right? I can pull nRT out front, and that leaves me with nRT ln, help me out, P2 over P1. Okay? All right, what we're going to do is we're going to use this as our starting point on Wednesday. All right, thank you. Have a good one. So let me also just point out, you may have noticed we're tossing a lot of letters around. It can be very confusing, so you have to own it. So spend some time making sense of the letters. Have a good one.